Hello and welcome to this video on solving polynomial inequalities. And this is immediately following another video I put out on solving quadratic inequalities, if you'd like to look that up. And what we're gonna be doing in this video is taking a look at a couple examples of polynomial inequalities and solving them in that algebraic method, the same algebraic method that was used to solve quadratic inequalities again in a previous video. So if you want to look that up to get a more refresher on that, see other examples where I use this algebraic method, please do. All right. So my first example is one that's set up nicely for me already. It's solve, and I have two examples for you today. And in both examples I have the same instructions. Solve the polynomial inequality. There's two of them, so there's one later, inequalities, but there's only one here. Solve the polynomial inequality algebraically and graph the solution set, right? Write out the solutions on a number line, show a picture of them. Okay, so the way this inequality is set up, it's I've got 2x minus 3 times x plus 4 times x minus 5 on one side is less than or equal to 0. And this is the way I eventually want to get my inequalities involving polynomials. I would like the completely factored polynomial on one side, which this is, right? And this would be a degree 3 polynomial, a cubic. If you were to multiply this out, you'd have a 2x times x, which would be 2x squared, and then if you took that 2x squared times this x, multiplied all the lead terms, the lead term over here would be 2x cubed. So I want a completely factored polynomial on one side and 0 on the other. Okay, this is my ultimate goal in these problems. Well, not my ultimate, maybe a few steps before the end, but I'd like to start off setting up the inequalities this way. Polynomial on one side, and then completely factor that polynomial if I can, and 0 on the other. Right. Then after this, okay, I'm trying to determine what values of x make this inequality less than 0 or equal to 0. Well, the fact that I have 0 over here is very important. I want 0 on the other side because we're going to be taking a look at the values that this expression on the left side takes. When you plug a real number into any expression, the result will either be 0, positive, negative, or undefined or unreal. Right? But being that this is these are polynomial expressions we're looking at, they're not going to be undefined for any real number input, and they're not going to be unreal for any real number input. So the value of this expression will either be 0, positive, or negative, and that's what I'm going to focus on. When do each of those things occur? So first, the first thing is I'm going to find where the polynomial equals 0, right? And then we'll determine where is it positive and where is it negative. All right, so we're solving this equation. When is this polynomial expression, this factored polynomial here, 2x minus 3 times x plus 4 times x minus 5, when is that equal to 0? And again, you can see why I want it factored, because if it's factored, it makes it real simple, right? You use that zero product property, right? The only way a product is equal to 0 is if one of the factors is 0. So, this first factor, 2x minus 3, when is that going to be equal to 0? When x is positive 3 halves, right? If I set that equal to 0, I would then add 3 divided by 2. So that's one solution to this equation. That's a value that when plugged into this expression would make it 0. So this would actually be a solution to my inequality. Right? When I plug in 3/2 for x, it makes the left side 0, and 0 is less than or equal to 0. It satisfies the or equal to part, right? The equals 0. So then same thing for this next factor. When is x plus 4 equal to 0? When x equals -4, right? It would subtract 4. And when is x minus 5, the other factor, equals 0? When x equals +5, right? So I find these solutions, right? I find out where is, once I've got the polynomial on one side, 0 on the other, I find what numbers make this polynomial equal 0. So 3/2, -4, and 5. All right, then what I'm going to do is I'm going to mark these numbers off on a number line. Pardon me. So I'm going to mark these numbers on a number line. Okay, so here's a real number line. And because there's this inequality involves only one variable, x, this one number line will represent possible values of x. And then something else I like to do for these inequality problems is above the number line, I like to write the expression that we're plugging into, right? This expression on the left side here is, 2x minus 3 times x plus 4 times x minus 5. I like to write that expression that we're plugging into above the number line, and you'll see why in a second. All right, so marking these numbers off. 3/2, that's 1.5. I'll just put some mark somewhere, say that's 3/2. -4 would be to the left of that somewhere. Right? There's -4. Just make sure things are in the proper place. The numbers that are less are to the left of the numbers that are greater. And then 5, +5. No, this is 3/2. It's 1.5. So +5 is greater than that. Then I mark off the numbers on a number line. And then, as I mentioned, I like to put the expression that we're plugging into, this 2x minus 3 times x plus 4 times x minus 5, above the number line, and write down what kinds of values we're getting when we plug in certain values for x. So when I plug in, -4 for x, the value of this expression is 0. All right, now be careful. This is not an open point. All right, this is actually the number 0. I know some of you, when you might think I'm graphing right now. I'm not graphing the solutions yet. All right, so this is actually the number 0. Okay, not an open point like on a graph. Right? The value of this expression when x is 3/2 is also 0. Right? And the value of this expression when x is 5 is 0. Okay. Now you see what these numbers do. All right. These three numbers, when I mark them on a number line, the real number line, break the real number line up into pieces, into intervals. In fact, it breaks the number line up into 4 different intervals. And what those intervals are, so it breaks the number line into intervals. So you have these numbers that are, to the left of -4 that I haven't checked yet, right? Less than -4. You have these numbers between -4 and 3/2 that I haven't checked yet. You have these numbers between 3/2 and 5 that I haven't checked. And then you have these numbers to the right of 5 or greater than 5. And in these intervals, right, the value of this expression is either going to be positive or negative, right? I mentioned earlier, when you plug numbers into a polynomial expression, the value you get back, the output, is going to be either 0, positive, or negative, right? Because it's not going to be undefined or unreal, right, if it's a polynomial. So we already marked off where the value of this expression is 0. Right, so in all these other intervals, it's going to be either positive or negative. And this also has something to do with the fact that the function is a polynomial function is continuous, but we're not going to get into the whole concept of continuity here. Just believe me when I say the value of the expression will be either positive or negative in each of these intervals. So that's what we're going to test. Right, so the next part. I'm going to plug in a test value from each interval. And determine if the expression is positive or negative. And that's all I care about, if it's positive or if it's negative. Because our inequality, right, we're comparing the value of this expression to 0. Right? This is the initial inequality here. Where is this expression less than or equal to 0? So all I care about is, is this thing negative or positive, right, when we're comparing to 0. Okay, so I'm going to plug in a test value from each interval and determine if the expression is positive or negative. And for positive, I'll put a big plus sign, or and for negative, I'll put a big minus sign. All right. So the way I do this is, I'll keep the number line, and here's the expression that we're plugging into. Now you can just I'll show you. I usually just do things on the number line itself. I just leave this picture up here. But I've also seen you can make a table with these intervals. So here's a table where I have in one column the interval, in the next column sorry, phone ring. Okay, so we have the back to the table, interval, and then I'm going to have a test value, right, some number from that interval that we're going to plug into the expression. And then just is the value of the expression positive or negative? Right. Okay, so the intervals, these intervals of numbers I mentioned before. Now we have the first one on the far left. I'm going to go left to right, low to high on the number line up here. These numbers to the left of -4, less than -4. That would be in interval notation. That'd be the interval from negative infinity up until -4. But again, I already know the value at -4. The value of this expression is 0 at -4, so I'm not including it right now. All right, so right now I'm just putting parentheses here. All right, now pick a value in here. Say x equals, you could do -5, -6, -1,000,000, -4.5. I think an easy one would be -5. All right, something that's less than -4. And then I plug it into the expression. All right, so I'm going to write the expression again down here. We have 2x minus 3 times x plus 4 times x minus 5. And when x equals -5, again, I really don't care about what the actual values of these expression is. I just care if it's positive or negative. So when I plug in -5, 2 times -5 is -10, minus 3 would be -13, right? Now you could do that, or just sometimes I've seen people write, this factor is negative, right? It is a negative number. Times, and then when I plug in -5 for x in the second factor, -5 plus 4 is -1. Again, I don't care if it's -1, I just care is it positive or negative. That is another negative factor. And then times, and then -5 minus 5 is -10, another negative factor. oops, sorry, should be parentheses, big parentheses, right? So we have a negative times a negative times a negative. Now again, I mean, you can easily say what this is, right? This would be negative, right? Because these make positive 13 times negative 10 would be negative 130. Again, I don't really care. I just care that it is a negative result. So back in my table here, for these values in this interval, test -5, the value of the expression is negative. Right? And what I like to do personally is back on the number line I drew here, above these values, plug in -5, -6, and you could do it for any of these. Plug in any of these numbers less than -4, the value of this expression will be negative, and I put a big minus sign above these numbers on the number line, telling me that when I plug these numbers into this expression, the output will be negative. Okay. All right, the next interval is the numbers between -4 and +3 halves. So that interval is this interval here from -4 to +3 halves in interval notation. Again, not including them because I already know their values at -4 and 3 halves, so I'm putting parentheses on those. Test value, again, you can use -3, -2, -1, -pi, 1, 1.4. I think an easy one though, in most cases, is 0. Right? The number 0 is in between -4 and 3 halves, and let's plug that in. All right, so when x equals 0, well, look, the first factor, 2 times 0 minus 3, that'll be negative. Again, I know it's -3, but again, I don't really care about the actual value. I'm just, is it positive or negative at the end? Then the next factor is 0 plus 4 is +4. So I have a negative times a positive, and then the last factor, when I plug in 0 for x, 0 minus 5, that'd be -5 or negative. And then a negative times a positive, that's a negative. And then a negative times another negative is a positive number. I would end up with a positive result. So back in my table, so this will happen, and this is just one value, but it would happen for any value in here, and you can try it out yourself. Plug in any number, -3, -2, -1, whatever, between -4 and 3 halves, and you'll see that you'd get a positive result when plugging it into this expression. And like I said, I like to do it back on the number line here. The numbers from -4 to +3 halves, when they are plugged into this expression, I get a positive result. So I'll put a big plus sign above those numbers on the number line. Okay, and let's keep going. The next interval. All right, the next interval is the numbers between 3 halves and 5. Right, that would be this interval here, from 3 halves to 5. Again, not including them, because I know their values 0. The value of the expression is 0 at those numbers, so parentheses on those. And I'll just take 2. Right, this is 1.5 to 5, so 2, 3, 4, 2.5, pi, whatever, square root of 2, I'm sorry, square root of 3, not square root of 2. But 2 would be nice. 2 is in there. When I plug in x equals 2 to this expression, first factor, 2 times 2 is 4, 4 minus 3 is +1. I get a positive factor, times 2 plus 4 is +6, another positive factor, a positive times a positive, and then 2 minus 5 is -3, that's negative. A positive times a positive will be a positive, and then times a negative, positive times negative is negative. Get a negative result no matter what I plug in that interval. Right? So again, try some other numbers if you want, if you don't believe it, but take numbers between 1.5 and 5, plug them into this expression, and the output, the result, will be a negative number. So again, I put a little minus sign here on my number line. All right, numbers plugged in from 1.5 to 5, plugged into this expression, will give me a negative result. And then finally, right, there's only one other space of numbers I haven't talked about. The numbers greater than 5, right, to the right of 5, and that would be from 5 to infinity in interval notation. Right, again, not including 5 because I know the value at 5 is 0. Plug in a value, a test value, say x equals 6, 7, 8, a million, whatever you want. As long as it's greater than 5. Now when I plug in 6, 2 times 6 is 12. 12 minus 3 is 9. That's a positive first factor. I'd get a positive first factor. Times 6 plus 4 is positive 10. Times 6 minus 5 is positive 1. I get a positive times a positive times a positive result. Alright, so for these numbers greater than 5, when they are plugged into this expression, you will get a positive number result. Great, and that takes care of every number on the real number line. You know the value of this expression is negative for all these numbers, 0 for negative when x is negative 4, positive for all these numbers, 0 when x is 3 halves, negative for all these numbers, 0 when x is 5, and positive when x is any of these numbers, right? So we've taken care of the entire real number line, and then let's actually get into solving the inequality, right? All right, so I'm going to cover up this test stuff, and the last part is actually solve the inequality. All right, so look back. Let's go back to the original inequality. Here it was. All right, and I'm going to keep my number line up there. All right. So here was the original inequality, right? That expression, the 2x minus 3 times x plus 4 times x minus 5, when is that less than or equal to 0? So look at the symbol. The symbol means a lot. If I'm looking for where is this expression less than 0 or equal to 0? Well, less than 0, having an expression being less than 0 means being negative. So that means I'm going to look for negative signs on my picture here, and also zeros, right? Because we want to look for what values of x make this expression less than 0, so negative, minus sign, or equal to 0. So I'm looking for where is it equal to 0 as well, these zeros that I put up above the numbers 5, 3 halves, and negative 4. All right. Or you could look at the table that I made as well. All right. Look at the table that I made as well. Oops, I forgot to put in positive there. All right. Or you could look at the table and look, hey, there's a minus sign. So these are solutions. These numbers from, that are less than negative 4. And there's a minus sign. So there's some more solutions, right? These numbers here from 3 halves to 5, and that's it. Right, as well as the negative 4, 3 halves, and 5, the one that make it equal to 0. Right, so when I say this, let's solve the inequality, here's the solution set. Alright, so the solution set, looking at my little number line here, looking for numbers that make this less than 0 or equal to 0. Well, that's these numbers here, right? So from negative infinity up to negative 4, negative infinity is not a number, so you always put parentheses around that in interval notation. Now, earlier I didn't put, I put parentheses around negative 4 because I knew what the value at negative 4 was. But let's think about, is negative 4 a solution of the inequality? And it is, right? It satisfies the equal to part. When x is negative 4, this expression equals 0. So I'm going to put the bracket, right, the rectangular bracket on negative 4 to indicate that it is a solution. It does satisfy this inequality. All right, but that's not the only place, right? So remember the OR symbol, that was that union symbol. So x could be any one of these numbers, or, and then not these, right, because those make this expression greater than 0, not less than 0. They make it positive. The other interval with negative outputs is this between 3 halves and 5. So from 3 halves to 5, I put 3 halves comma 5, and then I cap these off. Now, earlier I had parentheses, but remember, 3 halves makes this expression equal 0, so it is a solution. 5 also makes this expression equal 0, so it is also a solution. So both the 3/2 and the 5, right, and the numbers in between are solutions. So I put the brackets on those, the rectangular braces. And that's it, right? Those are the only numbers, from -4 to the left, and then from 3/2 to 5. Those are the only numbers that make this expression less than 0 or equal to 0. So those are the only numbers that actually satisfy the inequality. Those are the only numbers that are solutions of the inequality. I hope that makes sense. Now, this is one way to write the solution set. You could also write it in the set builder notation, right? The solutions to this inequality is the set of all values of x such that, and then I'm just going to write a little inequality to represent each of these intervals. This interval here means that x is less than or equal to -4, or, right, the union symbol or. And this is betweenness, x is between 3/2 and 5, including 3/2 and 5. So I have x is greater than or equal to 3/2 and at the same time less than or equal to 5 connected like this. So this is another way to write the same set, right? This interval notation here, this set builder notation, these represent the same set of numbers, the same solutions. All right, and then finally the graph. All right, if I were to graph, here's a number line. Now this time I'm actually making a graph. I'm drawing a picture of the solutions. And again, this is possible values of x. Here was, -4 and 3/2 and 5. And we said the solutions of this inequality are the numbers less than or equal to -4. So I'm going to put like a closed point or a bracket on -4, a rectangular bracket. And then all the numbers less than -4 are these numbers here, right? Or all the numbers between 3/2 and 5, including 3/2 and 5. So again, closed points on 3/2 and 5. Those are solutions, and then every number in between. And there's a graph of the solutions, right? A picture of all the numbers that, when plugged into this inequality, would make it a true statement. And if you want to test it out, right? And let me put this in a box. Here's the solutions and the graph of the solutions. Cool, right? And if you want to test it out a little more, be my guest. Try it out on your own. Plug in any number from -4 to the left. Any number less than or equal to -4. Plug in -5, -6, -7, -4.3, whatever, into this expression, and you will see that the number you get back will indeed be less than or equal to 0. And go ahead and plug in any number between 1.5 and 5, 1.6, 1.7, pi, the square root of 3, 4.9, 432, right? Plug in whatever you want, and you'll see that this expression will indeed be less than or equal to 0. And all the ones we didn't put, right? The numbers between -4 and 3/2, or the numbers to the right of 5 greater than 5, when you plug those in, it'll make this expression positive, which is not less than or equal to 0. It's greater than 0, so those are not solutions. That's why I didn't mark them off, right? And we saw that in our number line earlier as well. Great. All right, so again, this is the same procedure that was used in a previous video on solving, quadratic inequalities with the algebraic method, but, just extending it to here this was a degree 3, cubic polynomial equation, or inequality, sorry. All right, so I've got one more example. All right, where again I'd like to do this. I'd like to get the inequality to be in this form, where I take my polynomial on one side, 0 on the other, and then completely factor the polynomial if I can, and then go from there. All right, so my next example, and my last example for this video, is I'm asked to do the same thing. Solve this polynomial inequality, and then graph the solutions. All right, so this time I have it's starting off in a way I'd like. The polynomial, this is another cubic or degree 3 polynomial here, is all on one side, and then I have 0 on the other. But I'd like to try to factor this thing. All right. Now this is a polynomial with 4 terms, so I'm going to try factoring by grouping. All right. And I've put up a video in the past on factoring by grouping, or just look up factoring by grouping, and I'm sure plenty of other videos will pop up. Just check it out if you're unfamiliar with it, but I'm just going to go through it kind of quickly here. So I'm going to try factoring this by grouping, and that was where I, in parentheses put, the first, I break it up into kind of two parts, two halves. Put the first two terms, x cubed plus 7x squared, in the first group, and a big plus sign, and then in the second group, the next two terms, the negative 4x, and then the minus 28. And then we got greater than 0 still. Then you factored each half separately. The first half, they have these two terms have the common factor of x squared that I can pull out. I pull out x squared, and then what's left over when I remove x squared would be x plus 7 plus, and then these next two terms have the greatest common factor would be 4, but the lead coefficient in this second group is negative, so I'm going to pull out the opposite of that. I'm going to pull out negative 4. So I factor out negative 4, and if I remove a factor of negative 4 from these two, I have x plus 7 left over again. It still is greater than 0. And then if you look at the thing as a whole now, after you have factored each group, look at the thing as a whole, right? They both have this x plus 7 as a common factor. So that comes out, x plus 7 pulled out. And then what's left over when I remove a factor of x plus 7 from each term is x squared plus negative 4, but that's just minus 4. And I'm not done factoring it completely, right? It is factored, sure, but I'd like to factor the polynomial completely if I can. X plus 7 doesn't factor any further, but x squared minus 4 is one of those differences of two squares, right? This is x squared minus 2 squared. So that would factor to x minus 2 times x plus 2, or x plus 2 times x minus 2, whatever you want. Okay, so this is the way I like it. This isn't the answer, I'm just kind of bubbling it in here, because that's the way I like it. Alright, where I have the polynomial completely factored on one side, 0 on the other. Alright, so then the next part, if you recall from my last example, was we're comparing this polynomial here to 0. So I'm going to say, when is this polynomial equal to 0? Alright, so when is the polynomial equal to 0? So we're solving this equation. When is x plus 7 times x minus 2 times x plus 2 equal to 0? Right? I know we're going to figure out where it's greater than 0 later, right? Where is it positive later, greater than 0? But for right now, let's figure out where it would be equal to 0, and then we can figure out where it's positive or negative after that. Alright, so product, again, the reason I like it in factored form is because it makes this equation much easier to solve. I have a product equal to 0, and a product is only equal to 0 when one of the factors is 0. So x plus 7 would be 0 if x were negative 7. X minus 2 would be 0 if x were positive 2. Or another solution to this, if x plus 2 were 0, x would be negative 2, right? All three of these numbers are solutions to this equation. They make this expression on the left side of the inequality equal 0. So they're not solutions of the inequality, right? We're looking for numbers that make this expression greater than 0. These all make it equal to 0, not greater than 0. But they'll help us in the long run. Alright, so I like to, again, I put these on a number line. So here's a number line representing possible values of x. And then, like I said in the last example, I like to put above the number line, the expression we're plugging stuff into. So the x plus 7 times the x minus 2 times the x plus 2. Right. Now these numbers, right, we see that negative 7, when I plug in negative 7 for x, the value of this expression is 0. Again, that is not an open point, that is the number 0 this time. When I plug in negative 2, which would be to the right of negative 7, when I plug in negative 2 for x into this expression, the value of this expression is 0. And positive 2, right, which would be to the right of all these. Right? And then when I plug in 2 for x into this expression, I get output of 0. Great. All right. Okay, so here's where I'm going to do my test values. All right. So I see how these numbers, now I'm not going to make that table like I did earlier. I like to just do it on the number line myself. So you see how these three numbers again break up the real number line into four intervals. I have this interval from negative infinity up to negative 7, then from negative 7 to negative 2, got that interval, then from negative 2 to 2, between negative 2 and 2, and then from 2 to infinity, right, from to greater than 2, all those numbers. So four intervals again. So let's test an interval over here, all right, to the left of negative 7. How about negative 8? Easy enough, right? Now I'm plugging them into this expression again, right? X plus 7 times x minus 2 times x plus 2. And again, all I care about is, is the value of the expression positive or negative? So I plug in negative 8 for x. The first factor, negative 8 plus 7 is negative 1, so negative. And then negative 8 minus 2 would be negative. Negative 8 plus 2 would be negative. So I have a negative times a negative, which would be positive, these two, and then times a negative again, which would be a negative result. All right, so back on the number line, all these numbers to the left of negative 7 would make this expression a negative number. Right? So these numbers are not solutions, right? We're looking for values that make this expression a positive number, right? Greater than 0. So these are not solutions. All right, the next interval. Between negative 7 and negative 2. How about negative 3? So again, when I plug into this expression each of these factors, the first factor, negative 3 plus 7 would be positive. Negative 3 minus 2 would be negative. And negative 3 plus 2 would again be negative. So I have a positive times a negative, which would be a negative, and then times another negative, which would result in a positive number. All right, so I have, for these numbers between negative 7 and negative 2, make the value of this expression positive. So these are solutions, right? These actually make this expression greater than 0. And we'll write that later. All right, then between negative 2 and 2. All right, well, again, you can put negative 1, positive 1, but again, 0 is usually a nice, easy one to plug things into because it makes things disappear. Right? So for this third interval, between negative 2 and positive 2, I'll plug in 0. First factor, 0 plus 7 is positive. 0 minus 2 is negative, and 0 plus 2 is positive. So I have a positive times a negative, which would be a negative, and then a negative times a positive after that would be a negative again. All right, so I have another negative value. So if you plugged in any value between negative 2 and 2 for x, the value of this expression will be negative. Okay, and therefore not solutions to this inequality. We're looking for ones that make this positive. And then finally, the last interval to the right of 2, I'm going to plug in just positive 3. Any number greater than 2. All right, so 3 plus 7, positive. 3 minus 2, positive. 3 plus 2, positive. And positive times a positive times a positive, all positive, right? So any value I plug in for x that's greater than 2 will make this expression a positive number. Therefore, a solution, right? Any value greater than 2 is a solution to this inequality because it makes it greater than 0. And that's what I'm going to write out next. All right, so I'm going to cover up the test values here. So the solution set to this inequality. First, I'll write it in that interval notation. Remember, these numbers here, we're looking for where is this expression greater than 0? Where is it positive? So I'm looking for plus signs. Right? I'll even write that back up here. Look for plus signs, right? So where is this expression positive? Well, not for these numbers. All right. but they are for these numbers. So between negative, so from negatives, if I'm doing interval notation, I'll go from -7, comma to -2, and then we have to ask, are these solutions? Do I put parentheses or brackets on these? Well, -7 makes that expression equal 0, not greater than 0. Now, if this was greater than or equal to, that'd be great, but it's just greater than. So -7 is not a solution, so I put a parentheses on that. -2, same thing. -2, when plugged into this expression, makes it equal. You'd have 0 is greater than 0. That's not true. So again, it's not a solution. Parentheses on that. Now, that's not the only interval that makes the values positive. This one does too, right? So not between -2 and 2, but to the right of 2, right? So or, union, right? Or, and then from 2 to infinity, right? Everything greater than 2. And again, is 2 a solution? No. 2 when plugged in would make this 0 is greater than 0. No, that's not true. So 2 is not a solution. Again, a parenthesis on that. And infinity is not a number, so always parentheses on this. So this is the way I would write the solution set to this inequality in interval notation. Right? All of these numbers described here are solutions of my original inequality, right, which looked like this, right, going all the way back up here. So I could take any number. Let's go back to the original inequality now. So if I take any number between -7 and -2, say -6, -5, -4, whatever, plug it in, this will be a true statement. Take any number greater than 2, 3, 4, 5, a million, plug it in, this will be a true statement. And any other number won't be, right, won't make it true. So I could write it that way, or in that set builder notation. Right, the solutions to this inequality are any value of x such that, then here we have between this, right, so -7 is less than x and x is less than 2 at the same time, between, but not including, right, not less than or equal to, just less than, or, union, or, and then this interval here just represents the numbers greater than 2, right, x is greater than 2. All right, so this would be a way to write the solutions in that set builder notation. And we can make a graph, right? Single number line for possible values of x. And mark off these numbers that are mentioned here. There's again -7, -2, and +2 are mentioned in the solution set. And all the numbers, between -7 and -2, but not including them, right? So these are actually open points now, all right? Not the number 0. Right, these indicate, or you could put parentheses, right? But these are actually open points now, not 0. All right, so they indicate that the number -7, the number -2 are not solutions. But then every number in between is, right? So there's a graph, a picture of that interval, and then the other interval, right? The value is greater than 2, right? But not equal to 2, right? Again, so open point above 2 to tell me that's not a solution, and then all the numbers greater than 2, right? All the 3, 4, 5, and so on. Great, and there's a nice picture of our solutions to this inequality in multiple different ways, right? This interval notation, this set builder notation, this graph, pardon me, all represent the same set of numbers, right? All the numbers that make this inequality that we started with a true statement. Right, when I plug in any of these numbers for this expression to this expression will have a positive value. It will be greater than 0. Great. All right, so I think the big thing to take away from this in polynomial inequalities is, one, it never hurts, right? And you saw this with polynomial equations, quadratic inequalities. It never hurts to start off getting the polynomial all to one side and compare it to 0 on the other. And then, then what we did afterwards was, if you're able to, if you see how, factor the polynomial completely, because that'll make figuring out where that expression equals 0 a lot easier. Then once you've figured out where that expression equals 0, then you figure out where it's going to be positive, where it's going to be negative. And again, it's never going to be undefined if it's a polynomial. Right? It's either going to be positive, negative, or 0. And then once you've determined that, where it's positive, where it's negative, where it's 0, you can then easily see what the solutions of the inequality are, right? It all really depends on how that inequality symbol looks, right? If it's greater than 0, you're looking for positives. Less than 0, you're looking for negatives, and so on. Great. And as I like to say at the end of these videos, please do the best you can to try and learn the material on your own before you go looking for help. I have found over the years that people that take the time and the effort to learn something on their own tend to remember that material better and remember it for longer, and are more proud of it. So of course, read the material, right? Read through the author's examples, perhaps even try to work out the solutions to an author's examples before you see how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously do tons of exercises, practice problems, right? Practice makes progress. It's the only way to get better at anything. And check for solutions to those, if they're made available to you, just to check your work and to keep track of your progress. And don't give up on a problem or an exercise after just 1 or 2 attempts. Very often in mathematics there are several approaches or several ways that you can do a particular problem that'll work. So if after several approaches, several attempts at a particular problem or set of problems, if you're still having trouble, I would actually suggest to you to go back and read the material again, maybe even a 3rd time, more slowly, more deliberately. Take good notes, and maybe even organize those notes afterwards into a format that you can actually read and understand. Because if you've been working on problems as you should, you probably have a better idea as to what the author expects from you in that section, or what the author wants from you in that section. You'll see what the author finds is the most important material from that section. So when you go back and read it again, you'll know better what to look out for. You'll know what's the important stuff to look out for. And maybe even some things will pop out at you that didn't the first time through, or even the second time through. And it'll make working on the problems that much easier. Okay, but if after that, if after several approaches at the problems and several read-throughs of the material, if you're still having trouble, it is not a sign of weakness whatsoever to go looking for help after all that, after you've tried to help yourself. And that's what people are there for, right? To help you out when you're stuck, after a big effort on your part. So, ask a teacher, a tutor, a friend, someone in your class who knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos online, right? Videos like this one, or plenty of other videos out there that are better than this one. I assure you they're out there and they're easy to find. But just keep at it, right? Stay persistent, keep practicing, don't give up. And above all, and I think this is the hardest thing for most people, stay positive. Actually believe in yourself, believe in your abilities to make it through your struggles and failures and mistakes and frustrations. Because it's in those moments when you are struggling and having failures and making mistakes, it's in those moments that you have the opportunity to learn the most, and also to learn the most deeply. Because if you can persist, if you can persevere and work through your frustration, push past them, and eventually learn how to fix your mistakes for that material, you'll remember that material far better and far longer than someone who got it right the first time and just breezed through and never gave it a second thought again. Alright? So just stick to it. Alright? Be persistent. Keep practicing. Stay positive. And don't give up. And I just know you'll get it. I believe in you. Alright, and thank you very much for watching.